Good morning, everyone. We're just going to take a couple moments here while folks get connected. Welcome to this workshop series, the synthesis workshop series on perceptual models of dominant hydrologic processes across North America. Thank you for taking the time to join us today for this workshop. We're really excited about all of the synthesis and information that's going to come out of the discussions that we'll have here today. Before I hand things off to our speakers, I wanted to give a brief overview of Quasi while we're still getting settled and to kick things off for today. My name is Julia Masterman. My pronouns are she, her, and I'm the Education and Outreach Specialist for Quasi. Quasi is the consortium of universities for the advancement of hydrologic science, and we're a nonprofit organization funded in part by the National Science Foundation. Our mission is to empower the water community in advanced science through collaboration, infrastructure, and education. We seek to fulfill this mission in two main ways, through our data services and our community services. Our data and compute services provide tools and support for the entire data lifecycle, all the way from data discovery through to data publication and collaboration. Quasi hosts two data repositories for water science data, primarily HydroShare. It's the hope that by providing this infrastructure and this support, Quasi can help researchers formulate and execute their data management plans and be effective data stewards. It also helps meet requirements of funding agencies. The other side of our house, so to speak, are our outreach and community services. These include grants, workshops like this, a summer institute, and the National Water Center for graduate students, a virtual university, and more. So this is the first in a series of 5 workshops with a morning and an afternoon session. We'll hope you'll consider joining us for the other workshops in this series, or we'll share this with a colleague who may be interested in some of the regions that these future workshops will cover. So today we'll be focusing on the Eastern Coastal region, as defined in part by this map in the purple. So thank you so much for our conveners for putting together this series of workshops, and to CIROH, who is supporting this project. This morning, we will hear keynote speakers from 4 fantastic speakers. I'll be handing the mic over to Martin in a moment to describe this project in more detail, introduce our speakers for the day. Thank you for taking the time to join us today and to contribute your expertise to the synthesis activity. This afternoon, we hope that you will join a synthesis meeting. I was speaking to you, the attendees. You'll need to register for it separately, but all are welcome. That link will be in the chat in just a moment. If you have not already gotten the connection information. In the afternoon, we'll do a quick reminder of this morning's presentations and then break into breakout rooms to help continue to discuss perceptual models in these regions and subregions. Before we get started, a few logistical things. This webinar is being recorded and will be posted later on the Quasi YouTube channel. As an aside, the recordings for the afternoon synthesis meetings will not be shared publicly. Secondly, we ask that you use the Q&A functionality to submit questions to our speakers. Please feel free to add questions at any time and upvote any that are especially of interest to you. We will have time left over after each of the speakers to answer some questions and then try to get to as many as we can. And then there'll be plenty of time for more in-depth discussion in the afternoon session. Finally, we expect that all involved with Quasi events to uphold the Quasi Code of Conduct and promote and maintain a professional, considerate, respectful, and collaborative virtual environment. So thank you very much. This slide has a vague outline of today's agenda, in that we'll be starting with presentation, a brief overview from our facilitators here, followed by talks from Dr. Jamie Shanley, Dr. Margaret Simmer, and Dr. Kieran Harmon. Dr. Matt Cohen may or may not be able to join us today, but we thank him for his contributions as well to this project. And with that, I will pass it on to our facilitators. Thank you.
Okay, I'm just trying to share. Okay, and can you see my slides okay?
Yes.
Yep, it's okay. Okay, perfect. Well, just to start with, we'll talk about The need that we have when we're interested in predicting threats to water futures, it requires comprehensive models that synthesize our understanding of interactions between the natural and anthropogenic world. The key challenges can include quantifying sustainable water supplies, predicting water-related hazards, and understanding the role of water in the Earth system. And this challenge can often exceed the capability of entire modeling groups, entire agencies, and in many cases, entire nations. So community approach is needed. The US National Water Center, as part of the Office of Water Prediction, has risen to this need through developing different versions of the National Water Model. The initial version of the National Water Model used Earth system modeling approaches, where a land model was applied on a 1 kilometer grid, terrain routing applied on a 250 meter grid, routing on the NHD plus river network, and a level pool reservoir model. The prediction ecosystem had parameter estimation at gauge locations with limited regionalization, data assimilation based on direct insertion. This provides information for about 2.7 million river reaches, which extended the predictions from about the 3,600 points that were served by the river forecast centres. The initial plans for the National Water Model were very ambitious, with the plan for predictions of water quantity in year 1, water quality in year 2, and predictions of hypoxia in the Gulf of Mexico in year 3. This was really part of the hyper-resolution paradigm, with the attempt to have a higher resolution representation of hydrological processes. There's some commentary papers on the hyper-resolution paradigm from Eric Wood, late Eric Wood, and Mark Birkins, talking about the benefits of that paradigm. And the paradigm is really leading into digital twins that can provide a deterministic view of the world with the challenges of data integration and management, ensuring accuracy and fidelity, and interdisciplinary integration. These paradigms have received a fair amount of critique in the literature, with papers by Keith Bevan, Hannah Cloak, Florian Pappenberger, etc., talking about hyper-resolved ignorance, that we don't have the data to infer the parameters in complex models that are applied over large geographical domains. And very recent critique by Andreas Saltelli that was just came out a couple of weeks ago on digital twins. The main critiques of the hyper-resolution paradigm is that it does not perform well because there's not sufficient information and computing resources to infer the large number of model parameters, and that hyper-resolution models are not sufficiently agile to simulate observed processes in specific regions. So in response to those limitations, the NOAA Office of Water Prediction has been advancing the next generation water resources modeling framework. The motivation is that the siloed approach to modeling, if we're using lumped bucket style models or hyper-resolution process-rich models, does not adequately consider the diversity of modeling approaches at various levels of spatial and process complexity. And it's difficult to identify a single model that's best everywhere, best at everything, and best all the time. So the approach in NextGen is to construct a deterministic multi-model mosaic that can represent the diversity of hydrological processes across the North American continent. And this model mosaic, the idea is that different models can be running across different corners of the continent. The challenges in this approach, and the reason why we're here today, is that land hydrology is immensely diverse across the continent. That arises from the combinations of the forces driving hydrology, namely the climate, the vegetation, the soil, the geology and topography, the land use and direct water manipulations. And if NextGen is to realistically predict local hydrologic states and fluxes across a rich hydrological tapestry, we need to know what processes matter, where, when, and how. That's why we're here today. So the scope of the project that we have that's supported by the Cooperative Institute for Research to Operations in Hydrology is to define the dominant hydrologic processes for a continental mosaic of distinct landscapes. So the research entails iterating on the following tasks through regional workshops. We've got the first regional workshop today, an interactive website, and continental domain synthesis. And the tasks that we're working on are first to produce a continental map of hydrological landscapes that's defined through the juxtaposition of hydroclimate, terrain and geology, vegetation, land use and management. And then also to develop perceptual and conceptual models for each unique landscape and the hydrologic mosaic. So we've made a start on the first one, and we're here today to talk about developing perceptual and conceptual models for the eastern coastal region. And the idea is that this process synthesis will provide the theoretical support that's necessary for next-gen developers to simulate the salient processes and features of each unique hydrologic landscape across the North American continent. And this feeds into a larger body of literature as to how can we improve the theoretical underpinnings of models. So what are the key elements of hydrologic theory that we need to incorporate in models? How can we incorporate this theory in models? And how should we evaluate competing hydrologic theories across scales and locations? So what we're interested in today is the first of these research priorities. The work that Wouter Knerman has done beginning to define hydrological landscapes has been taking information on topography, primarily elevation and slope, to identify landforms across the continent, information on aridity, seasonality and snow fraction to provide a classification of hydroclimate across the continent, and information on agriculture, land cover, and soil depth. In the initial work that we've done, we've been able to identify some hydrologic landscapes, but in doing so, we will recognize that a lot of the important hydrological processes can be organized by river basin, and many people are working on multiple hydrological landscapes across each river basin. So now we're moving into the regional workshops to understand what are the dominant hydrological landscapes in the eastern coastal region in this workshop, what are the dominant processes, and how can we think about representing those processes in models, the appropriate spatial scale, etc. So here's an overview of the workshops. Julia mentioned this. We're in the first workshop in the eastern coastal region, and our overall goal is to improve the theoretical underpinnings of models by synthesizing process understanding across large spatial scales. And the idea is that defining perceptual models of hydrologic behavior can provide insights into process dominance, and from there we can select appropriate models for the region or make targeted improvements if no appropriate model is available. Of course, this is very, very difficult. The traditional tactics used in hydrology, such as detailed analysis and modeling of individual catchments, makes it difficult to generalize results to large domains and other regimes. We've seen a lot of commentary in the literature on this topic over the past couple of decades. The concerns are, is it even possible to generalize hydrologic behaviors given the unique character of individual basins? Do we lack the necessary information on climate, topography, vegetation, soils, and subsurface structure that's required to develop powerful and exceptionless explanations? And are the problems of underdetermination so pronounced that we cannot move beyond explanatory pluralism? Where we're going here, we do acknowledge uncertainty, underdetermination, and the difficulty to generalize, and we're embarking on the synthesis effort to systematically formulate, organize, formalize, encode, and evaluate hydrological theories or hydrological process explanations. And we're arguing that the community's made tremendous advances over the past few decades in our capability to explain and predict individual processes, process interactions, patterns, and scaling behavior. Our process explanations or theories are currently scattered across research groups and are not yet widely incorporated in hydrological models. And finally, advances in hydrological modeling are possible by identifying consistently observed behaviors across research watersheds, formulating the laws that govern macro-scale hydrological behavior, and unifying process explanations across watersheds. So we're really looking forward to the group coming together today so that we can begin to make some progress on these very difficult questions. So for now, I'll turn over to some of my other co-conveners, Yang Fan, Hilary McMillan, Valda Knurban, etc., to see if you've got anything to add to what I just presented.
I'll just add my welcome to everybody here. It's great to see so many participants online. I'm really excited about this project. I know we have so much great information about individual watersheds in our regions. And so the aim with this webinar and meeting today is to really understand, how can we interpolate the information that we have between those like points on the map where we have really great hydrologic information and begin to draw conclusions over large scales. So great, and looking forward to the talks.
Yang, I think you wanted to say something as well.
I don't have anything to add.
Okay.
But I'm happy to introduce the speakers now.
Yeah, very good.
So Julia, what's next on the agenda?
First up, I believe we have Dr. Jamie Shanley.
Right. So we have invited 4 keynote speakers to really get us started. And these are experts in catchment hydrology, biogeochemistry. And they have great insights to offer. They have worked in the fields and different sites for many of them, some of them for decades. And they have great intuition, great understanding. The perceptual model or conceptual model, depending on how you look at it, are really a sort of a cartoonish abstraction of dominant hydrological processes. And our goal, as Martin said, and as Hilary said, is to put dots on the map, connect the dots, and finding out where and how, what processes are first order, second order, etc. So we can have a really systematic way of deciding what processes to represent where at what scales. Okay, those are some of the critical questions that we will work toward at the end of the day in the afternoon section, especially. And for now, we have 4 keynote speakers. But Dr. Matt Cohen has a family emergency, so he will not join us today. He will be focusing on wetlands, so we will have to get his input later. But we have 3 keynote speakers this morning, Dr. Jamie Shanley, and Dr. Margaret Zimmer, and Dr. Kieran Harmon. We'll start with Jamie, Dr. Shanley, and Jamie, while you share your screen, you can, if you possible, I will have a brief introduction here. Dr. Shanley is a catchment hydrologist and biogeochemist situated at the USGS New England Water Science Center based in Vermont. And so he has been working in the Sleepers River watershed, which is experimental watershed where the saturation overland flow concept was born. And he continues that legendary work. And he also studies the fluvial transport of carbon and nutrients from mountains to the sea, which is a pretty broad scale. And so, he will be talking about today the dominant hydrologic processes in the northern part of the northeastern region. So the sub-region is the north. So Dr. Shanley will share with us his insights on processes in the northern part of the region where cold weather process, cold climate processes are important. So Jamie, take over.
Do you hear me okay? Yes, okay, great. I was on mute. Great, so I'm gonna launch into my PowerPoint here. Let's see. Okay, you see my slide? I'm not hearing anybody, but I assume you're seeing my slide, and I will start going.
Yeah,
So,
looks good.
great. So this is a few pictures from my main watershed, Sleepers River in northern Vermont. We have a great picture of my favorite process here on the left, saturation, excess overland flow. And on the right is a view from sort of the top of our watershed out across the Connecticut River to the White Mountains of New Hampshire. You can see in the background, we claim we have the best view of New Hampshire and all of Vermont from our watershed. So what I'll be talking about today is mainly processes in the glaciated Northeast. So this map shows the kind of the area that was glaciated in the United States. That line extended down to Long Island is a glacial moraine, and it extended down into most of northern Pennsylvania. So Sleepers River here is designated here by the SR. And I'll be talking a little bit about two other watersheds, some work we're doing on Mount Mansfield and also Hubbard Brook. And you can see we're kind of in the heart of this area, although we're kind of more mountainous than most of the area. As this, well, the next slide will show, but just to talk a little bit about Sleepers River, has been going since 1958. It was one of the original agricultural research watersheds. Two of the luminaries who worked at the site, Eric Anderson from the National Weather Service, he did a lot of radiation energy balance modeling of the snowmelt process. And from all that work, he developed the Snow 17 model, which is a simpler temperature driven model based on his knowledge of the radiation. And that is still used today in the National Weather Service of snowmelt flood forecasting, even though he developed it in the late 60s, early 70s. And then, of course, Tom Dunn worked at Sleepers River and developed a lot of his ideas about saturation, excess overland flow. And I got a couple of slides on Tom coming up. And the USGS has been at the site since 1991. We're the first entity that brought some biogeochemistry to the site, which is kind of one of my main focuses. We're working particularly with carbon in the context of global change. So here we are in northeastern Vermont. We're in the Passumpsic River Basin, which is a tributary to the Connecticut River. The Connecticut River forms the border between Vermont and New Hampshire, and then flows down through the middle of Massachusetts and Connecticut into Long Island Sound. And as you can see on the left here, Sleepers River is in the Kittredge Hills, which is one of these parallel ranges to the Green Mountains, the spine of the Green Mountains, the highest mountains in Vermont to the west, and the White Mountains in New Hampshire to the east. These peaks in New Hampshire get up to 2,000 meters. The Kittredge Hills are only not even quite 1,000 meters. And the Green Mountains are about 1,500 meters. And the Adirondacks of New York are a little off the left of this map, but you can see them a little bit on this map, these purple shading, and they're about 1,700 meters. So we're a little bit lower in the middle of all these higher mountains, but a great place to look at processes coming off the headlands into lowlands, and we have a diversity of land uses in our watershed. As shown here, here's a map of the entire Sleepers River watershed. It's 111 square kilometers. We do most of our work up here in the forested headwaters, and here's a blow up of that W9 watershed, which is 41 hectares. But we have this nested basin system at Sleepers River, which is really nice. W3 and then W5, and each one is a little over an order of magnitude larger as you go downstream. And as you get into W3, you start to open up into some pasture and corn growing. And that just continues as you go downstream. But still, the entire basin is 67% forested. So a lot of forest, and we're looking mainly at forested processes. There is one other catchment that we work at, the W2, which is mostly pasture. And I've got one slide showing processes from there. Here I've got some photos of the 4 basins we work at, from the headwaters down to next larger to W5, the largest basin. Oops. And these all have these concrete weirs that were built in the late 50s when apparently they had a lot of money and could put a lot of structure on the landscape, and they're all still in really good shape. We're only using 4 out of the original 16, but they've all held up. Okay. So, I wanted to show on the map where Tom Dunn did his experiments, and they were actually right on the edge of the watershed near its outlet. So he worked in a small tributary to the main Sleepers River right here near the outlet weir. So these are photos that Tom sent me, and these are his words. He sent them in a PowerPoint, and I just took them right out of his PowerPoint. He dug these trenches at the base of this hill slope to see like what level the water was emanating during flow events, with the main conclusion that you don't really get a lot of flow until you saturate right up to the surface. And so this was 45 years ago he was doing this work. And we've verified that saturation overland flow is the main process going on here. But what we've been able to add is isotopic work showing that a lot of that water is old water that had been in the system prior to the event. So we got Tom back to Sleepers River in 2001. So what is this, 30 some years after he did his experiments. And he's standing now in the median strip of Route 2. And the hill slope that he did all of his experiments on was completely removed to widen this highway from 2 lanes to 4 lanes. He's in the median strip there saying, where's my hill slope? And I want to superimpose one of the photos I just showed. And I think this is taken from the same angle as this more modern photo. And I think that's the same ridge in the background. And you can see that indeed his hill slope was taken away for progress. He knew this was going to happen actually when he did the experiment. It happened not long after. And he was kind of excited about that because he could see what his hill slope was made of. But it was dense basal till mainly. This is all glacial till. It was pretty easy for an excavator to get out of there. But Tom's work resulted in these 3 landmark heavily cited papers in Water Resources Research about the partial contributing area and saturation overland flow. And we were happy to get Tom back into sort of an update on the hydrology at Sleepers River, this paper from 2015, where he was a co-author and provided a lot of insight into our sort of more modern interpretation of hydrological processes, which I'll be getting into in this talk. So now, fast forward to much closer to the present and the National Water Model. So we actually have a project going now with the University of Vermont with funding through the CIROH initiative of the collaboration between NOAA and the University of Alabama. And this project's being led by Andrew Schroth and Beverly Wemple. And we have this great postdoc, Mirce Morales, who provided us this figure. And it shows how poorly the National Water Model does in these montane headwaters. The focus of this project really is to improve the National Water Model in the montane headwaters where we work. And this is actually at the outlet to Sleepers River, the W5 111 square kilometer scale. But the blue line is the National Water Model prediction. And you can see it doesn't do very well. The black line is the actual observed flow during this. This is a snowmelt period. So what Mirce has been doing is applying machine learning techniques to take the National Water Model output and adjust it to the black line reality of what we see. And she's getting much better results. Now, I should preface this by saying that she was well along with this paper, which is just about to be submitted, using version 2.1 of the National Water Model. Version 3.0 came out, I believe, this spring, but she was well along with 2.1. So we continued this work with 2.1. Maybe 3.0 does a lot better now. And I really have not been too engaged in Mirce's work, and I know that there have been problems with the input. And I don't know to what extent this poor performance is based on poor input or poor process representation. Okay. So at Sleepers River, we have a great isotopic record, and the bright red line is the O18 in precipitation. And you can see it varies between about -25 and +5 in O18 per mil. And the 4 different weirs we look at are the colored lines in the middle, and you can see how damped the isotopic signal is. And that just shows the amount of mixing and the lags that happen within the landscape. But when we look at individual events, as I mentioned earlier, we show a predominance of old water. The light blue is the new water inputs. And you can see during the very highest flows, when you get a lot of snowmelt runoff into the stream, you will get a fairly high percentage. But overall, the new water percentage is fairly low, on the order of 20% or so. So this large, long duration snowmelt hydrograph is composed primarily of older pre-existing water. The one exception to this was that pasture catchment I showed a photo of earlier, where the 1 year where we had, I know this is a very old slide, 30 years old, but that's when we were doing most of our work in the pasture catchment. And we had a lot of great data from them, but we had this one really heavy frost year in 1993, where we had a low snow cover. The frost got quite deep, and the meltwater, the snow meltwater signal is in red and the stream is in green. So the extent that the stream water, the green points, bend down to the red points, which is the meltwater isotopic signal, is an indication of how much new water is feeding the stream. So in this high frost year, the water was running off directly over land surface, and most of the stream water was new water. In this more normal year, a lower frost, all that water was infiltrating, and we only had a slight deflection of the stream O18 signal towards the meltwater. So much less new water, predominantly old water in this year. So this is a little unusual, but when you get a heavy ground frost in a small area, it can lead to a lot of new water. We found at a larger scale, even in this 1993 year, we just don't see this effect. This is because you had a small watershed and runoff really close to the stream. We find in the larger watersheds that water always finds tree line somewhere to infiltrate. And ground frost, we don't think is a very important process controlling flow in the Northeast. I just want to add to that, the Hubbard Brook seems to have deeper ground frost than we do at Sleepers River. We're like about the only two places that consistently measure this in the Northeast, and they don't see much influence either. I'll talk a little bit more about that when I get to show their perceptual diagram. But the transmissivity feedback, so Tom Dunn was showing that experimentally, just observing the runoff and the saturated extent. We in our Headwater W9 watershed, we did some hydraulic conductivity measurements, and we verify that as you go up in the profile, we had a series of nested wells here, a deeper well into the till down to bedrock that screened over that whole till interval, and then some nested wells higher up in the soil zone. And these blocks are from each of the three wells. As we go up towards the surface, the hydraulic conductivity gets higher and higher. So that kind of confirms what we see with the saturation overland flow. As you get higher up into the profile, that water can move more quickly. Here's some data from a couple pairs of nested wells. This one on the left is in the riparian zone, and these two nested wells here, you can see the water table is close to the surface even prior to snowmelt. And it just doesn't have very far to go up. In fact, here the head is actually above land surface. And so you're always going to have saturation overland flow like year round in this setting. But high on the hill slope, the groundwater table is quite low, here more than a meter below the surface. And during snowmelt, it will dramatically rise up to close to land surface. And in these nested wells, you can see this well higher up in the profile remains dry until the water level gets up to that point, and then it rises with it. And we take this as evidence that we just don't have much water perching in this watershed. And in fact, with 20 pairs of these nested wells, we only saw evidence of perching in 2 of those pairs. So we think that is not a very important process here at Sleepers River. When I talk about Hubbard Brook in a little bit, we think it is more important at Hubbard Brook. And just kind of another way to look at these 2 wells, we see this interesting hysteresis when we plot the groundwater level versus the stream discharge. And in the riparian zone, this hysteresis is clockwise. So the groundwater level is rising and peaks when the stream peaks, but then as the stream is going down, the groundwater level is going down more quickly. So at the same discharge on the falling limb, the riparian water level is lower than it was on the rising limb. And so we take this as evidence that the riparian groundwater is really controlling flow in the stream. In the upper hill slope, even though we have that dramatic rise in water level, we see that it keeps rising after the peak flow. So it's contributing a little bit later and maybe in a less important way, the groundwater from the upper regions of the watershed. So the action is down by the stream. Here's a map of what I'm calling it partial contributing areas from W9, but this is really based on areas that are 3 meters above the nearest stream level along a flow line. So it's a pretty good indication of areas that could saturate, and it is a pretty close representation of what we see on the ground. And just one interesting point here is that a lot of our streams emanate out of these headwater swamps, but that we have a really wet riparian zone. and a lot of saturation right around the streams. So before I get to my perceptual diagram, just for some context, one thing we need to explain is how do we generate these high flows in the summer when we know that our saturated areas, which I showed here, have really contracted. There's just not a lot of percentage of the watershed that's saturated. And yet we get some of the highest flows during the summer months. So part of my perceptual model will try to explain this phenomenon. So here is, and sorry, Hillary, this is my best attempt at a perceptual model, and it's left wanting. My daughter just entered art school in college, but she left before I could get her help on this, unfortunately. But there's room for improvement, and we'll keep refining it. But so here I've shown 2 different times a year, the snowmelt with the water table up here, and summer with a much lower water table. And I'm really showing it because this is what we observe. It really does come up close to land surface throughout. I have it in the soil profile. This is soil and till. It's above into the soil profile, the whole length of the hill slope. So we got rapid flow. You saw the higher hydraulic conductivity in this upper soil zone, and then it comes into the emanates and causes saturation overland flow. So we have pretty rapid flow down the slope and then onto the surface and into the stream even more quickly. Whereas in summer, we see kind of low, mostly matrix flow that slowly feeds the stream. And at Sleepers River, this till is very fine grain. It's mostly in the fine silt fraction, so it really holds water. There's a lot of storage, and it releases water quite slowly. So this really sustains space flow. And I'll contrast it with Hubbard Brook in a minute, because Hubbard Brook, the same sized watershed at Hubbard Brook will dry up almost every summer, whereas we have 43 years of record at this catchment at Sleepers River, and we've never gone to zero flow. So a little bit of a difference there. As to how much water we may be losing to the regional aquifer out of this watershed, I'm sure it happens. We don't really see much evidence. We have sort of a very reasonable amount of ET. If you calculate ET as precipitation minus runoff, it's about the same every year. So this is not a water limited system. It's about 500 millimeters every year. So we may be losing a little bit, but that's just about the amount of evapotranspiration we'd expect. So I don't believe we're losing much. I'll just jump ahead and say that at Hubbard Brook, they have pretty much the same thought, that they're not really losing much to the regional aquifer up in their headwater systems. Now, to get at that question of what's happening in summer, here I've kind of, because you can't show much at the scale in the soil here, I've done blow-ups of the soil until here, one for snowmelt and one for summer, showing this the soil zone up here down into the till. So during snowmelt, the water table is up into the soil zone. We have this transmissivity feedback, shunting water down the slope quite rapidly. At some point, this emanates and flows over the surface. We have snowmelt feeding this aquifer, which has risen up close to surface through both macropore flow and matrix flow, represented by these arrows. So that's pretty straightforward and get a lot of flow during snowmelt. In the summer, the water table's way down here. So how are we getting those high flows? Well, we're invoking interflow, which is a process of water infiltrating and reaching some sort of barrier a layer with lower hydraulic conductivity, or it could even be just a contrast in the permeability where you have this high hydraulic conductivity in the surface, and suddenly it drops off to a lower value. And so the water in those intense thunderstorms is coming in too quickly, and it shunts off over that lower permeability. There's, of course, going to be some leakage through that will ultimately recharge groundwater, but this has got to explain the bulk of those high flows we see in the summer. Okay. Now I'm going to take another view of this hill slope. So this is sort of the 1D down from the top of the hill slope to the stream. And this would be about a 200-meter reach across. Now I'm taking another, well, I just want to say that for that interflow to reach a stream, that's one of the conundrums. So if we're not very saturated, how does that interflow actually get to a channel? And we're invoking this channel expansion where the streams become not too hard to get to because there's more of them as the catchment wets up. And so we're invoking that interflow, and maybe it just doesn't have as far to travel to get to a channel. And thanks to Julian Klaus and Kevin McGuire for this figure, because this is, what Kevin says is happening at Hubbard Brook as well. So I want to take another view. Again, that was the perceptual diagram was the 1D hill slope view. If we look sort of diagonally up the hill slope here, we have planar hill slopes, and then we have these hill slope hollows or convergence zones. And we don't believe, even though the groundwater table comes up close to surface, we don't believe we're getting a lot of flow to the stream in these planar hill slopes. And that's because the chemistry of this water just isn't right to explain the stream chemistry we see. However, the water in these hill slope hollows does have the right chemistry to explain the stream chemistry. So we think that water kind of flows along the base of these planar hill slopes till it reaches a convergence zone, and that's where we get the flow to the stream. And I have a sketch of the chemistry here. So these orange points are the stream chemistry. These red points are that hill slope hollow water or that convergence zone groundwater. It's a little more concentrated. This is silica versus calcium, but it's kind of in the right plane to explain that stream water if you just dilute it with a little bit of snow melt. Whereas all of these other points up here, these are the groundwater up in the hill slope, and it's got too much silica to explain the stream chemistry. So we just can't see that water being a big player in the stream flow generation. And again, even though that water table, and this is a plot I showed earlier, gets up close to surface, it doesn't have the right chemistry. So we're banking on this hill slope hollow water to be contributing to stream flow. The one other watershed I said I'd talk about before we move to Hubbard Brook, we have a study going at Mount Mansfield, which you may have heard of, the Stowe Ski Resort. And we have a paired watershed study there where one watershed drains the entire downhill ski area. There's our downhill skier. The other watershed is mostly pristine. It does have cross-country trails on it, so I have my cross-country skier here. The watersheds are fairly similar in all aspects except the development. And of course, being an alpine ski area, we've got snowmaking. So all the snowmaking water stays in the watershed. It's taken out above the weir, pumped back up onto the slopes. So we're not gaining water from outside the basin. And yet we do have more flow in this watershed. And so we think we may have some fracture flow input in this side more than the cross-country side. Also, we have thicker soils on the cross-country side, the more pristine side. So we don't have as much fill and spill going on. We also think with this development, not only do we have the snowmaking adding more water to this side, we also have these compacted surfaces from the trail construction and all the machinery that goes over these trails. So we do think we see more surface runoff on this side as well. So that's a little bit of the anthropogenic influence that we see and that we need to take into account in our hydrologic modeling. The other thing that goes on in these alpine basins is that we have these thin soils near the summits where it's very easy to generate saturation overland flow. Even without much contributing area, you just don't have much to saturate, so it saturates pretty readily. And we see some rapid flow up in the headwaters. So moving to Hubbard Brook, while I was talking about that overland flow and thin soils, I'll just mention that first at Hubbard Brook, because they see that there as well. They have very thin soils near the summit, which has a lot of bedrock near the upper elevations. And what they have there for soils is basically just an organic horizon that in many cases is lying right on top of bedrock. So this is important in their DOC story, but it's also important for the hydrology. So a lot of this, they'll see a lot of flow up here that with that expanded channel network I showed in one of those slides that Kevin provided, we see that contributing to stream flow. I mentioned frozen soil, like they do have more frozen soil at Hubbard Brook, but they don't think that's a big player in the hydrology. They think it's not really concrete frost, it's more permeable and the water does infiltrate. The channel at Hubbard Brook is more in size than at Sleepers River, so they don't have that sort of classic gentle riparian area bleeding into the stream. And that means that they do have saturation overland flow, transmissivity feedback working like at Sleepers River, but it's a lot more jumbled up with the big boulders and things around the channel. It's not quite as textbook as it is at Tom Dunn's Sleepers River, but it is an important process. It's just kind of intermittent up the channel. The interflow process, very important there, especially generating flow in the summer. And here they've depicted it. This is kind of copied from one of Kevin McGuire's drawings where he shows the interflow perched. They definitely do have perching there. And he shows the interflow kind of perched over a hydraulic conductivity contrast. And he shows it going right up to surface on one of his diagrams, and then kind of running off as saturated overland flow. And so Kevin would call even this transmissivity feedback, he would call that interflow as well. In my mind, I like to kind of differentiate that because this is groundwater this is sort of a bottom-up process, saturation from the bottom up rising up and causing the transmissivity feedback, whereas I've visualized the interflow as kind of more of a perched thing, or in the case of Sleepers River, it's perched there as well. It's hard to see that perching in field observations. Like I said, we don't see it in most of our nested wells, but we do think it's happening. Yes, so, and again, like I said, they don't think they see much loss to fractures, although lower down in the Hubbard Brook Basin, the USGS has done a big groundwater study there and show that fracture flow is really important. So it's coming from upslope somewhere, but they don't see much evidence of it because they do have some boreholes in near this catchment, and they just don't see the fractures. So I did want to touch on the sort of larger scale regional hydrology, and I apologize, there's not much hydrology in this slide, but I did want to touch it. We talked about this in our sort of pre-meeting meeting, that when we do the national water model, it covers the whole area, and there's a lot of urban area in New England. So I've depicted a little bit of that, a lot of farming, which we have that a little bit at Sleepers River, but I didn't really get into it because with farms, you have tile drains, ditches, overland flow on compacted surfaces. One thing I didn't get in here is we have also dams and reservoirs. So a lot of different things affect the hydrology as you get downstream, including runoff over, urban impervious surfaces or even towns. Just a lot of hard surfaces here that cause more rapid runoff, and that helps feed the major rivers. But the forest is still 65% of the Connecticut River Basin. So there's a lot of woodland hydrology that you need to take into account that affects what's going into Long Island Sound. So I want to close. No idea what my time is. I think I might be over, but Julia said I have 40 minutes. So just to close up here, I think it's my last data slide. I just want to talk about the last 2 years where we have had unbelievable high flows all during summer. So this red line, which is the same on both of these pluses, 2023 and 2024, this red line is the highest flow we've saw in 33 years of studying this catchment. And there are 16 additional years of historic data. And there was one time that flow got above the red line back in 1973. That's this purple mark here. But in 2023, we had 4 events that exceeded that level. And this summer, we had 2 more that went over that. So this is a new regime. I just want to mention, and it's very spatially variable. We have a lot of rain in one spot and not so much a few kilometers away. So this peak right here, there were 20 centimeters of rain just in the town of St. Johnsbury, which is just 2 miles away from Sleepers River. Sleepers River hardly even saw it. So that could have been another peak above the red line. Just a lot more flow. And it's just been crazy. I'm sitting in my kitchen because our office was flooded out and we're still not back in it from this flood in 2023. So quick take homes that Tom Dunn nailed it. Saturation overland flow is the story at Sleepers River, but we added water isotopes to show that old water dominates except in these unusual frozen ground conditions. But you really need interflow, these flow over low permeability lenses to explain the high flows in summer. A lot of our groundwater comes from these headwater superficial aquifers, which feed the regional systems. This low permeability till has high storage and rations out base flow over time. And with climate change, snowmelt discharge is going down, but these summer flows are ratcheting up, these really intense flows. And this could be a real challenge for the National Water Model, where you really have to get these highly spatially variable inputs right, because one of the goals of the National Water Model is to be an early warning system to downstream communities. So that's what I got, and I'm happy to take any questions if I left any time. Thanks.
That was awesome, Jamie. Exactly what we hope to hear. And I'm going to, for the audience, if you have a question for Jamie, you can they unmute Julia themselves and ask the questions, or they must type into the chat box?
Yes, you will need to type it into the chat box. But if you want to join us this afternoon, you'll have a chance to have more face-to-face discussions.
Okay, so they cannot ask questions directly. Let me see
Yeah.
in the chat box.
Or please enter them in the Q&A. So you'll be able to see the questions that are coming in via the Q&A as attendees.
Oh, yes.
as well.
Okay, here we go. There's one question from Shan Zudima. And does the interflow process help explain or confuse the observations of old water making up the majority of stream flow in summers?
Yeah, that's a great question, Shannon. It confuses it a little bit in my mind, but as a lot of studies have shown, even the water in the soil zone, and we're really talking about the soil zone here with the interflow, even that water can be old water. I mean, there's quite a bit of storage in the soil, and it's still, you're pushing that out. There's a lot of piston flow going on, and even that water, when you think about it, there's so much there compared to what's coming in that it's not too big a surprise that can be old water as well. I've never sampled these huge storms. I would imagine that it just does get swamped out. There's so much new water coming in that I imagine if we were able to sample one of these record-breaking storms, we would probably see more new water than we see in your typical summer thunderstorm.
Okay, I'm going to jump to the chat box. There's a question from Larry Band. Thanks to the great talk, Jamie. What is the evidence for the interflow as a major process? Are there direct measurements with nested piezometers or crest gauges? You did not mention the potential for micropore flow activation at high precipitation intensity.
Yeah. That's right. So, well, I think that kind of does go along with the last question. You are activating a lot of those micropores with that high, that just large amount of rainfall coming in. So I think it's a combination of micropore and macropore. I'm not sure, was there another part of that question I may have missed?
Are there direct measurements with the nested piezometers?
Well, the nested piezometers just measure the saturated, zone. So, macropore and micropore could be feeding the saturation. So, yeah, we can't really differentiate that from our nested piezometers.
Okay, so I'm going to jump back to Q&A from Kevin Bishop. A comment regarding the summer-winter differences. The intensity of rainfall can be greater than snowmelt. Snowmelt is just very sustained. This would support your explanation. I think I'm not seeing all of his comments.
Well, I think it was just a comment and not a question, but
right.
Yeah. Yes, very good point. Snowmelt is sustained. And yeah, it's just long duration. And that's why that water table can build up and sustain. It just has this constant input, even though the water keeps running off, it just keeps being resupplied. And yeah, one thing I didn't mention is a lot of that can be return flow. You're not only getting the direct input over that surface, but you have a lot more coming from upslope as well.
Well, next question from Kieran in the chat box. What controls the depth at which interflow occurs? How does the till get broken up and become sufficiently permeable? First, what controls the depth at which interflow occurs?
Yeah, well, that's just the depth where you have the permeability contrast or a low permeability lens in the soil.
Doesn't necessarily to be soil and till interface.
It often is the soil till interface,
Okay.
but yeah, we see, I think it can be up into the soil at times. And the way Kevin has illustrated it at Hubbard Brook, he does show it being within the soil zone.
And how does the till get broken up and become sufficiently permeable?
It doesn't really. I mean, we do have some fracturing within the till, especially when things get really dry. We can see cracks opening up in the soil and sometimes down into the till. But the till doesn't really get broken up. It just, and it's just not very permeable. So it's that sort of that slow feeding of the base flow through micropores, mainly.
Okay, here's the earlier question from Kevin. I couldn't see. Now it shows. Do you have peatlands or other wetlands in your landscape that need, what it's moving again. Do you have, now this keeps jumping up and down. Do you have peatlands or other wetlands in your landscape that need to be in a perceptual model? Very good question.
Yes, well, I did sort of put them on the perceptual model. We tend to have these the biggest wetlands, like the only place I'd actually call peat is in these headwater swamps, these areas high up in the watershed where the streams actually head. Those are sort of the origin of the streams. So the role they play in stream flow, by the time it gets down to the weir, I'm not sure it's really significant. In fact, a lot, like in the summer, you'll see the streams emanating from those wetlands, but they don't even make it to the weir a lot of times. So that water is infiltrating in other places downstream. But on the other hand, the whole riparian zone at Sleepers River, and I earlier referred to it as kind of a textbook where you just have a gentle slope to the stream that just really saturates up, and that really does behave like a wetland where it's just saturated a lot of the time. Even in summer, it does contract, but it's definitely part of the model. That's really what's driving a lot of the saturation overland flow.
Okay, I think Julia said we are out of time. Is that correct, Julia?
Yep.
All right. So thank you so much, Jamie, again. And it's hard to get a round of applause, but we're only showing the panel, the speakers, but I'm sure there are a lot of questions. Please, down there, please save those questions for the afternoon discussion, and we'll have ample time to chase the questions to the bottom. Okay, so now as we transition to the second speaker, who is Margaret Zimmer, and please, Margaret, share your screen. Just a few words about Margaret. Margaret is a professor, associate professor now at University of Wisconsin-Madison. She started at University of California at Santa Cruz and did some wonderful work on the California coastal range, the deep weathered zone, the storage, and hill slopes, and basically the critical zone forms and functions. And she's a watershed hydrologist and geochemist. And she focuses on water storage and flow paths in the critical zone in the Appalachians and Piedmont, today's talk, and because she did her PhD in this area. So she will share her thoughts on flow paths, particularly barriers and conduits in the southern to mid-Atlantic subregion of the East Coast. So Margaret, take it away.
All right, great. Thank you so much, Ying, for that introduction. It's great to be here today. I'm excited to hear all of this morning's presentations and to participate in the discussions later this afternoon. So I was allocated about 30 minutes this morning to talk a little bit about some ideas I might have that might help you all develop a perceptual model for the eastern coastal zone of the US. I've decided to focus this presentation mostly on giving a few ideas for you to consider, specifically surrounding hydrology in the southern to mid-Atlantic watersheds. So Ying just provided a great introduction to my past, but I wanted to just reiterate a couple points for why I'm talking about what I'm going to talk about today. So I completed my PhD in 2017 at Duke University. I did a field-based PhD dissertation, so I spent about 70% of my time over 4 years out in the Duke Forest woods, chasing raindrops around hill slopes. I studied how critical zone structure can influence streamflow generation specifically. So the Duke Forest is located right outside of Durham, North Carolina. It's located in the Piedmont region of North Carolina, and this is a satellite site to the Calhoun Critical Zone Observatory. So both of these research sites are located in relatively flat landscapes with deep, highly weathered soils. I should note that the Duke Forest is underlain by slate terrain, and Calhoun is underlain by granitic gneiss. So there's a few differences with these two research sites. And I should also note that once I graduated in 2017, I did move out to California, which is a very, very different landscape. So since 2017, I've been thinking a lot more about tectonically active, really jumbled, very steep oak savanna landscapes. And then just a couple weeks ago, I transitioned to being a faculty member at UW-Madison. So I've been thinking just in the last few months about landscapes in the upper Midwest, particularly agricultural landscapes. So while I'm going to talk a lot today about Piedmont hydrology and hopefully expand a little bit beyond the Piedmont into the Appalachian Mountains and a little north and a little south of Duke Forest and Calhoun, I also want to say that I've been thinking a lot about other landscapes, and so I think they might influence my reflection back on these systems as well. But I really, really enjoyed spending so much time chasing rain down hill slopes in North Carolina during my PhD, because I think the Piedmont landscape is such a unique and exciting landscape to work in. I love this graphic from Gannon et al. 2022, which shows USGS stream gauges across the eastern US, color-coded by a streamflow flashiness metric called the Richard Baker's Index. It's just a flashiness metric where higher values, so those blue values represent gauge streams that have flashier streamflow behavior, so they see more rapid responses in streamflow in response to precipitation incoming. And so what you'll notice here in this graphic is that in the Piedmont region, so the middle part of North Carolina, South Carolina, Virginia, all the way up to Maryland, those streamflow dots are a little darker than the regions to the right and to the left of them, so the coastal plain and the Appalachian Mountains. And so this represents higher flashiness or more flashiness in these Piedmont streams. So although they're much less steep than Appalachian Mountains, we see really, really responsiveness in these landscapes. So this make it really an interesting place to study. And I'll get a little bit more into what I think are the dominant mechanisms for driving that really flashy response in these relatively low relief landscapes. Okay, so that's hopefully a little bit of background onto why I'm talking about mid-Atlantic and southern Atlantic watersheds today. I'm going to focus this talk just on 3 takeaways. I'm excited to see what questions and discussion comes out of these three ideas. I'll say that these aren't original ideas by any means. You may even consider them oversimplified, or maybe you disagree with them, which would be great because it'll add some, I think, exciting discussion. But these three takeaways really stem from observations that I took away from my time at the Duke Forest during my PhD. So the first takeaway that I'm going to talk about is that these landscapes in the eastern US are typically thought to be energy limited landscapes. I'm going to argue today that they aren't always energy limited, and that that's going to really influence our perception of how they operate. The second takeaway that I'm going to talk about is that these are really highly weathered landscapes. We have some of the oldest soils in the US located in these watersheds. And this highly weathered subsurface, in particular, the critical zone subsurface, is going to allow for development of barriers in the subsurface as well as conduits that are both going to slow or stop the vertical flow of water, enhance lateral flow paths, or create opportunities for deep water storage in these landscapes. And then the last takeaway that I want to talk about is about the land use history. So these landscapes have been heavily worked through time. Particularly, these landscapes have been historically agriculturally dominated landscapes, and that has left a really deep imprint on hydrologic processes. Not to mention the Southeast US and the Mid-Atlantic region are places where populations are booming, and we're seeing a lot of new development over the last many decades that is leaving a new imprint on hydrology in a potentially, in some ways, in similar ways, in some ways, different ways to the agricultural imprint. Okay, so let's go ahead and dive into the first takeaway from this talk. And that's these energy limited landscapes aren't always energy limited. So you may recognize this graphic in the bottom left of the slide. This is the Boudico curve. This is a way that we can categorize or organize a key function of our landscapes. So on the x-axis, we have potential evapotranspiration over precipitation, and on the y-axis, we have actual evapotranspiration over precipitation. If you were to calculate either of these metrics for a watershed of interest and plot them on this diagram, your system would probably fall somewhere along that gray curve. If it falls to the left side of the diagram, that would signal that your landscape is a energy limited landscape. So there's plenty of precipitation to fuel the evapotranspiration needs of these landscapes. So we typically think about these landscapes as green, wet, maybe more lush landscapes with perennial streams. So plenty of water storage in them to feed our streams year round. If your watershed of interest plots more to the right along that curve, we're in our water limited category. So this means that there isn't enough precipitation to meet the evaporative demands in these particular climates. So we typically think about these as our drier landscapes, maybe less green, maybe less lush. These landscapes may also be places where we see more non-perennial flow or stream flow that may stop periodically, maybe in the driest months of the year. So typically we think about our watersheds falling somewhere along these curves. Why this is important is because of typically the streamflow regimes that we might align with whether our watersheds are energy or water limited. So Jamie mentioned in the Northeast US, they typically think about their watersheds, Sleepers River, for example, as an energy limited landscape. So this is, I think, a really great way to categorize the flow regimes in landscapes. So we can think about Calhoun Critical Zone Observatory and where it might fall on this Boudico curve. And I've actually taken an average water year and plotted it on that curve. And you can see it falls nicely in the energy limited portion of that Boudico curve. However, if we dive a little bit deeper into the hydroclimate data of Calhoun CZO, we start to see a little bit of a different picture. So in the top panel, we have mean precipitation through time over several decades, shown in those gray lines, and then the average precipitation shown in blue. You can see that the precipitation through a calendar year is relatively consistent. In the middle plot, we have evapotranspiration. Here you see that in winter months, evapotranspiration is low and it peaks in the summer months. You can see that there's a much tighter relationship year to year of evapotranspiration than there is of precipitation. And then if we take the difference of precipitation and evapotranspiration, what we see is that in our winter months, we have on average, a positive value on the y-axis, meaning that we have more precipitation coming in than we have of evaporative demand. And then in the summer months, when we see that big uptick in evapotranspiration, we also see a negative value on our y-axis on the bottom plot for P minus, or for precipitation minus potential evapotranspiration, suggesting that we're not getting enough precipitation to meet that heightened demand of evapotranspiration. And so if you think about what this may mean for storage or how these systems may be operating on, say, like the Boudico curve, you could classify loosely Calhoun CZO as being relatively energy limited in the dormant season or the winter season, and being water limited in the summer season. And this is, of course, ignoring any storage that is in the watershed that may help alleviate deficits in precipitation coming in. Okay, so let's dive a little bit more into why it matters if a system is energy limited or water limited within a water year. When we often think about the role of water storage in watersheds, we often relate it to runoff. And so this is an example plot of runoff on the y-axis and storage on the x-axis. This is looking at monthly runoff at Calhoun Critical Zone Observatory. And here we see that as storage increases, we see an increase in runoff. So the ability for a watershed to increase storage or for it to lose storage will dramatically impact how much stream flow is able to be released from the watershed. You can also see that there's almost looks like there's two arms to this relationship. So we see at higher storage, so about above 200 millimeters of storage, we see that there's a more steep runoff storage relationship and a less steep. And that has to do with the type of precipitation and the intensity of that precipitation coming into the system. And so instead of looking at this as an aggregated plot, we can look at it as a time series instead. And this might help us better understand what exactly is happening with those two arms of runoff versus storage. And so what you're looking at here now is one normal water year for Calhoun CZO. On the primary y-axis on the left, we have storage. And on the secondary y-axis on the right, we have a runoff ratio. The gray bars represent monthly runoff ratios, and the black dots represent event-based runoff ratios. And then we have a brown line that represents the storage through that through time, through that individual water year. And I've color-coded this plot, or I haven't. Grande et al. 2022 color-coded this plot by the different phases of storage. So whether you have a precipitation exceeding evapotranspiration, and so you have an increase in storage with that light blue, whether you are in a plateau period where perhaps your precipitation or your storage has been maximized, or your precipitation and your evapotranspiration are relatively in balance with each other in that darker blue, or if you have a loss of storage through time, so your evapotranspiration exceeds your precipitation, and that's in red. And you can see if you look at the monthly runoff ratios or your event runoff ratios, you can see that there's slightly different behavior, whether you're in your wet up period, your plateau period, or your dry down period. We typically see higher runoff ratios or more runoff for a given event in your plateau period or in your wet up period, and you see lower values in your dry down period. And so hopefully this showcases that our streamflow regimes change within a water year, and the relationship between precipitation and evapotranspiration, or its resulting storage, is going to influence how those runoff regimes behave through time. And this isn't unique to Calhoun. We can look at a few other sites across different climates to see really similar behavior. So shown here are 3 other sites located across the globe. On the top, we have Laquillo, which is a research site in Puerto Rico. Below that, we have Lower Hafren, which is a research site in maritime Wales. And at the bottom, we have Tilden, which is a research site located in central coastal California, which is a semi-arid landscape. And if we look at the behavior of storage in normal representative water years in these different research watersheds, we see that they behave similarly to Calhoun in that we have periods of wet up, we have periods where there's a plateau in storage, and periods of dry down. So meaning our storage is decreasing. And if you track what those black dots are doing or what the gray bars are doing, we see that runoff is typically, or runoff ratios are typically higher in wet up or plateau periods, and typically lower during the dry down periods. And so we think that it's important to be considering if watersheds are not just energy limited or water limited on longer timescales, like annual timescales, but it's also potentially valid to be thinking about how watersheds behave within water years. So seasonally, how they're behaving in terms of the relationship between precipitation and evapotranspiration, or what storage is doing, and how that relates to stream flow. Okay, so next I want to talk about how the degree of weathering in mid and southern Atlantic watersheds influence how water moves. So I wrote that highly weathered critical zones enhance both shallow barriers and deep conduits for flow. I'm going to focus mostly on shallow barriers and less on deep conduits, but I think our next speaker will talk a bit about deep conduits in some of these landscapes. Okay, so we can start by thinking about the deep soil profiles at Calhoun Critical Zone Observatory, which are pictured on the left. These are field scientists out at Calhoun digging really deep pits to characterize the soil and saprolite in these landscapes. You can see from these pictures that the soil is this really beautiful, rich red color that's highlighting their degree of weathering. And you can see that they're just very, very deep, highlighting not just that the soils themselves are very weathered, but they've weathered into very deep profiles. These pictures also pair really nicely with the graphic on the right, which is a graphic that I pulled from a relatively recent paper that was looking at the role of landscape age on the degree of soil weathering. And this graphic is showing the fraction of sodium remaining within soils across the US. And darker colors represent soils that are really highly weathered, that don't have a lot of sodium remaining. And so you can see that the Southeast is just a literal hotspot of weathering and very, very depleted soils, particularly for sodium. Okay, so I want to now talk a little bit about some observations that I saw during my time at the Duke Forest that relate to how the highly weathered critical zone in this landscape may influence stream flow generation. So Jamie Shanley showed some nice graphics in his talk previously, showcasing also soil hydraulic connectivity with depth. So it's interesting, and this is something that we should probably discuss later this afternoon, is the role of hydraulic connectivity in soil profiles, and whether we see dramatic changes in soil hydraulic connectivity with depth or more gradual, and how that could influence stream flow generation. So in the graphic to the left, I am showing saturated hydraulic connectivity values in those open white and closed black dots in two different soil profiles at the Duke Forest. I've also added dashed lines to represent where we see breaks in soil horizons. And you can see that generally we see pretty dramatic shifts in soil hydraulic connectivity with breaks in soil horizons. And so we were interested in trying to understand how those pretty dramatic breaks in hydraulic connectivity might influence flow paths in our hill slopes. And so we instrumented a headwater catchment highlighted in that darker black outline in the gray shaded zone of our watershed. And we outfitted this headwater catchment with nested wells and piezometers and nested soil moisture instrument nests. We also had weather stations and a flume represented with the red dot at the watershed outlet. And I'll touch on it a little bit in this talk as well, but we also put in a stream gauging station downstream of this headwater catchment in our larger watershed. And that's located represented with the light blue dot. Okay, so I mentioned that we installed nested wells and piezometers. We installed them in line with our breaks in soil horizons. And I think I have a graphic on the next slide to showcase that. Before I get into that, I just want to show an example of the precipitation, stream flow, soil moisture, and runoff response in our headwater system in an example water year, or about a year and a half of data. So in the top plot, we have precipitation with the hanging blue bar graph. In the gray, we have soil moisture through time, and the black line is evapotranspiration. On the bottom plot, we have runoff on the primary y-axis, and we have runoff ratios, and the runoff ratios are represented with those dots, and that's on the secondary y-axis. And so I think a big takeaway from this graphic is that there are really two streamflow regimes in operation in this landscape. And so you can see that in the runoff ratio circles in the bottom plot, there are periods of time where those runoff ratios are very close to zero. And then there are periods of the time where they are much more elevated. And they're much more elevated in periods where we have continuous flow, so we have base flow. And they're much more muted in periods where we lose our base flow, and any stream flow that occurs is in direct response to precipitation events. And you can see that if you relate the timing of the heightened runoff ratios or the diminished runoff ratios, it coincides with really dramatic behavior in our soil moisture time series and our evapotranspiration time series. So times where we have base flow and higher runoff ratios are also times where our soil moisture is quite elevated and our evapotranspiration is low. In periods where our runoff ratio is really diminished, those are periods where our evapotranspiration is high and our soil moisture is low and very responsive to precipitation events. And then, of course, it's important to note that our precipitation is pretty uniform across the year, at least on a monthly average. Okay, so this coincides, or this, I think, demonstrates what Grande et al. In their 2022 paper showed, where runoff responses are really strongly tied to storage dynamics, which are really strongly tied to the relationship between, you know, your precipitation and evapotranspiration demands. Okay, so we tried to explain those streamflow regime shifts in the summer and winter based off of what we saw in our hill slope hydrology. So I want to just take a moment to show you some graphics that we put together to showcase what we saw. And so on the left graphic, I just have a schematic showing our nested wells and piezometers in a representative hill slope. You can see the dashed lines represent the interfaces between A, B, and B and C, and then also refusal depth for our hand augering. And then on the right plot, we have our precipitation and runoff time series on the top plots, and they're just the same time series in all three plots. And then in the bottom plots, we have our groundwater elevations from those different nested wells. And so the left groundwater time series is from our lower hill slope position, very close to the stream. Our middle plot is from our mid hill slope position, and then our right plot is from the upper hill slope position. And each one of those jagged lines represents the water table depth for those different nested wells and piezometers. And so right away, you might notice that there's some separation in the water table depths for those different wells. And that showcases that we have perching occurring, especially it's really evident in the upper hill slope location, where our intermediate well is disconnected entirely from our deeper well. So the gray line and the black lines are disconnected all the time. In our mid-hill slope, we see that disconnection occurring parts of the year. So when our base flow is not active and there's only storm flow occurring, that's periods where we also see a disconnect in our shallow and our deep groundwater. And in periods where we have base flow and we have higher runoff ratios, that's periods where we have a connection between our shallower and our deeper wells. And the same is true for our lower hill slope positions as well. And so if I try and bring together that data into a perceptual model, we really have like two dominant cases. So again, on the right-hand side, we have just like a schematic of our nested wells alongside an example water table time series. And so in our first case, this would be periods where we have high catchment storage. This would be the dormant period of the year where we have base flow activated and we have high runoff ratios. And these are periods where our deeper water table is connected with our shallower water table. These are periods where all of the landscape is contributing to stream flow. And then we have another period of the year, which is when our evapotranspiration is increased, our base flow is decreased, our catchment storage is low. We don't have sustained flow, we just have event-based flow, so ephemeral stream flow. And here we see our groundwater levels, our deep groundwater levels are low, generally disconnected from our shallow perched water tables. And based on looking at hydraulic gradients across these hill slopes, we generally see that water is moving away from the streams. So these are periods where we have losing stream behavior, and water that is contributing to the stream flow is just coming from shallow flow paths, presumably from perched flow paths in the shallow soil. So I think this contrasts a bit with Jamie, or some of Jamie Shanley's work that showed that transmissivity feedback was a dominant process. Here, I think we would categorize this more as interflow, because at least in case B, because this is not necessarily deep groundwater entering shallow flow paths. It's instead precipitation entering the hill slope and moving laterally to the stream. Okay, I mentioned briefly that I talk a little bit about how these headwater systems relate to downstream systems. I just want to show you some graphics that relate the runoff ratios of the our entire basin study area relative to our headwater study area. And so that's shown in the graphic to the right. We have the entire basin runoff ratio on the y-axis and our headwater catchment runoff ratio on the x-axis. Here, and I have a one-to-one line shown in the dark straight line. I have the plots duplicated with different colors. So the top plot represents that deeper groundwater level. So if there's a darker green, it represents your higher groundwater levels. This would be in wintertime. And blues would represent, or even yellows represent when your groundwater levels are lower. And then the bottom plot is an active surface, active like stream drainage network density. So this is the activation of the stream network. And in either case, of course, we see higher runoff ratios when either our stream network is more activated or when our deeper groundwater levels are more activated. But I think what is a really interesting takeaway from these plots is the shape of this relationship between our two catchment sizes. And so I think one big takeaway is that the runoff ratios don't fall necessarily on the one-to-one line. Instead, you generally see higher runoff ratios at the headwater catchment scale than at the entire basin scale, and that there is some threshold response. So you see increases in runoff ratios of your headwater catchment without increases in your runoff ratio at your entire basin until you hit a threshold of about 0.5 runoff ratio for your headwater catchment. And then all of a sudden you see a more linear response. I think potentially Kieran Harmon might talk a little bit about the role of deep soils in storing water. I know Matt Cohen had planned to talk about that in his Southern watershed focused presentation. But I think this relationship, this like non-linear relationship is really driven by the lowland system acting as a deep sponge at lower storage conditions. Okay. And then I just want to take a moment to scale out a little bit. And, I started this presentation looking at or showing you this graphic of the streamflow flashiness metric across the Eastern US. And so I want to just highlight another paper that compared this flashiness of the Piedmont catchments to the streamflow response in the Appalachian Mountains. And so here we're looking at 70 USGS streamflow gauges categorized into either the Appalachian Mountains in green box plots or the Piedmont region in purple. And I think the takeaway I want to show here is that through time, over 20 plus years of data, what we end up seeing is that the percent difference of a watershed's response from mean annual base flow is much more variable in our Piedmont catchments than our Appalachian mountain watersheds. And so what I mean essentially from this is that those purple box plots are farther away from our zero flat line than our green box plots. And so this is telling us that the Piedmont catchments show much more responsiveness to changes in precipitation than our Appalachian Mountains. I think this is probably because of the shallow barriers across the Piedmont that stop water from really being stored in these deep soils as much as places like the Appalachian Mountains. Okay, and then in the last couple minutes, I just want to touch on the last takeaway from this talk, which is historic land use has left a really deep imprint on the hydrology. And so these are pictures of historic as well as current landscape of the Calhoun Critical Zone Observatory. So the Southeast USA has had really intensive agriculture and it's just really decimated the landscapes and changed them. They've left very big gullies and removed topsoil and exposed much more clay-rich soils. And you can see this imprinted on the landscape shown in the bottom left picture. You can really see those gullies still existing even in the early 2000s. I think I'm almost out of time, so I'm gonna go ahead and start to wrap up by just highlighting just how prevalent this historic land use has been on our stream networks and our stream flow behavior. Jefferson and McGee did a field-based study where they mapped about 100 channel heads in the Piedmont region of North Carolina, and they plotted the contributing area and the local slope associated with those stream channel heads and calculated a relationship between contributing area and local slope. And they found this relationship to be much less steep than the literature values that other people have developed from similar field studies and similar landscape types. And so essentially that suggests that the channel network extent may not reflect current processes, and instead it might reflect a former hydrologic regime, meaning that this intensive erosion in this landscape may have allowed for channel heads to persist in lower contributing area zones because you don't need as much contributing area if you have really rapid runoff. In this study, they saw that there was some recovery in the landscapes already. So these big gullies are starting to get sediment deposited, and new channel heads are forming farther downstream of these relic channel heads. And so this has been occurring over the last few decades. And so these stream networks are starting to recover and reflect more of this more recent hydrologic regime. Okay, and I think I'm out of time, so I'm going to stop here. And if there's time for questions, I'm happy to take them.
Thank you so much, Margaret. And okay, I'm going to read some questions out to you, Margaret. And so this first one is from Sun. Is soil water considered as water availability, quote unquote, when assessing a site is water or energy limited? That's the first part. Even in Vermont or Hubbard Brook, P can be less than PET in the hot summers. The Butico is for long-term annual means. The Southeast is indeed energy limited when assessing at annual scale. Annual or seasonal ET is mostly controlled by PET, rarely affected by precip overall. Margaret.
Yeah, I recognize that using the Butico curve could be controversial because that is a like a framework used for longer timescale categorization of how watersheds function. I guess the point I'm trying to make is that we should make sure that we're thinking shorter timescales, and in fact, watersheds that may be energy limited on longer timescales might have seasonal variability in the relationship between precipitation and evapotranspiration that might really impact the storage conditions of that landscape. And we may see even uniqueness in runoff storage relationships because of whether you're gaining storage or you're losing storage because of this relationship between precipitation and evapotranspiration changing through time.
And the second question from Gasan as well, regarding the flashiness of Piedmont and Appalachians, how climate ET differences affect the contrast? The geology is different, but does climate?
Yeah, climate probably does affect the here. Yeah, I skipped over this slide, but this might be somewhat informative. So on the x-axis, we have annual precipitation, and on the y-axis, we have a minimum annual daily runoff, so our low flows. The purple dots represent like average conditions for all these Piedmont catchments up here. And then the green dots represent average conditions for our Appalachian Mountain stream gauges. And so right away, you can see that the minimum annual daily runoff is higher in the mountains. And you can also see that many of these gauges report higher annual precipitation as well. And so they are wetter landscapes, which may explain some of the differences that we see in the Appalachians versus the Piedmont. But you'll also notice that in watersheds that have relatively similar annual precipitation, you still see a pretty different minimum annual daily runoff, which suggests that, yeah, climate probably does play a role. But I also think that it's probably some like biophysical control as well.
We're running out of time, but I would like to give the audience a chance to answer those questions. I'm just going to push a little bit. From Hillary, it seems as though high runoff ratios preceded increases in storage. Does this imply something about causation?
Sorry, can you say that one more time? My internet did something
Yes,
funny.
it seemed as though high runoff ratios preceded increases in storage. Does this imply something about causation?
Oh yeah, it very well might. Yeah, so it could be a threshold response. It could be where that water is originally coming from. Say like you have a lot of perched water contributing at first, like maybe that storage zone fills up with water before all of a sudden you have a contribution from deeper sources. Yeah, that certainly could be reflecting some causation, and I think we should definitely dive into that more.
From Larry Band, a very interesting talk, Margaret, was your ET time series from the nearby flux towers. Have you considered how much of the stream flow loss downstream at the Duke Forest was from seasonal recharge of the critical zone or riparian transpiration? First is your ET series from nearby flux towers.
Yes, it was. It wasn't from the exact years where we were also measuring stream flow and precipitation. They were from the flux towers, but from like 5 years prior. However, we took like averages for the period that the flux towers were active, and the standard deviation is very, very low. So we just assumed that that held true for our study period as well. There wasn't really riparian vegetation in these landscapes. There's not like an obvious riparian zone. However, I do think that there's a lot of recharge in the lowlands that's causing that nonlinear relationship between runoff ratios at different scales.
From James Helgren, super interesting presentation, thinking about our community goal for better simulation fidelity. Your slides made me think of this question relative to the interannual variation in water and energy limitation on a site. How much do we know about how the anthropogenic influences would alter the balance? For i.e., if we were to draw these plots from data in the 40s, how would that compare to the plots you showed?
That is a great question. I don't know the answer to that. I think that would be a great discussion question for this afternoon, but I am certain humans have really influenced that balance.
Right. I have to cut. Last question, Nate Jones. Julia said, last question, please. Thanks, Margaret. A great talk. In your work in the Duke Forest, you highlighted the role changes in vertical K-set, saturated conductivity on lateral fluxes to the stream. Can you comment on how heterogeneity in soils and K-set may impact emergent patterns of runoff response at the watershed outlet?
Great question, Nate. I guess it depends on exactly what you mean by heterogeneity. If you're meaning that potentially these impeding layers are not like continuous across all hill slopes, or from like the upper hill slope to the lower hill slope, or if you mean something else, I'm not entirely sure. But yeah, I think heterogeneity in soils could certainly influence what we're observing. I think that there's a strong enough stream flow regime pattern persisting that there must be some continuity in these impeding layers, even though we didn't punch holes in the ground everywhere to confirm that.
Thank you so much, Margaret. That was fantastic. I'll give it lots of thoughts to talk about this afternoon. In the last hour, we're going to have Kieran Harmon from Johns Hopkins University. And Kieran, please share your screen. Kieran is associate professor at Johns Hopkins University, and his research focuses on CZ hydrology, geochemistry, and landscape evolution. His work is not quite tied to a particular site or region, but more on the analytics and the synthesis level. He has thought about a lot about modeling complex systems to get the first order insights, and he will share his thoughts now with us. Kieran, the floor is yours.
All right. Thank you very much, Ying. Actually, I'm going to talk today about my backyard watershed a bit, so which I haven't presented a lot of work on in the past. We've been doing worked there for about 10 years. It's a very well-studied watershed before us as well. But I want to share some work with you that's quite a lot of which is unpublished, but some of which it is. The sort of two halves. This first part is going to be sort of talking about the perceptual model of this part of this watershed that we're looking at, and then I'll talk at the end about some modeling, some landscape evolution modeling and things based on that work. So this is actually a picture of the watershed. This is my student Cassie Cosins, who contributed part of this work. So before I get started, I should say that most of the hard work in here was done by other people, my students and collaborators, and they prefer it when I don't go out in the field because I make trouble. I guess I should start by sort of talking about a big picture question that I'm interested in, which is relevant to this question of process dominance, which is trying to say, well, we can go out and we can make lots of detailed measurements of a watershed and try to understand how it works today. But if we want to extrapolate that across the landscape, we have to understand something about, other places and how they have come, how, what properties they have, and perhaps thinking about why landscapes have the properties that they do could be a useful part of a framework for extrapolating these perceptual models across the landscape. And so by better understanding the origins of the physical structure that makes up the landscape and potential feedbacks between flow and structure, we can perhaps do a better job of thinking about process dominance everywhere. And sometimes people talk about this in terms of like a Darwinian approach to hydrology, thinking about the origins of things rather than just the mechanisms at play today. And you might describe a Darwinian approach to hydrology as one where you try to understand the patterns of variation in populations of hydrologic systems, very much like these workshops are designed to do, and then develop theories that explain those patterns in terms of the mechanisms and conditions that determine their historical development. In other words, think like a geologist, not an engineer. I'm particularly interested in sort of a relationship between hydrologic process dominance, surface topography, and the subsurface architecture and hydraulic properties, and those things are going to feature a lot today. A really nice example that's been around for a while, again, Tom Dunn appearing again, is this figure from 1978, sometimes called the Dunn diagram, which was, I guess, Tom Dunn's attempt to synthesize together process dominance and why it varies from place to place, or at least how it varies from place to place. The horizontal axis being one of sort of climate, vegetation, and land use, with Hortonian overland flow sort of dominating the arid and disturbed regimes. And then variable source areas dominating sort of the humid climates and dense vegetation. And once you're in that part of the world, which is where I think we are mostly situated today, some aspects of topography and soils become really important. So at one end, you've got sort of thin soils, gentle concave foot slopes, wide valley bottoms, and that's where you get this sort of saturation, excess overland flow, Sleepers River type behavior. Whereas at the other end, where you have steep, straight, convex hill slopes, deep permeable soils and narrow valley bottoms, then this subsurface storm flow may dominate, even if the peaks are produced by something more like saturation excess. And so the question is, well, if we think about this relationship between these different hydrologic processes and the topography and soils, what explains that relationship, right? How can coevolution explain the relationship that's implied between these processes and these structures? So I want to take you to my backyard just outside of Baltimore. I'm mostly going to talk about this watershed up here, Pond Branch, Baseman Run, which is located on the schist that makes up a lot of the Piedmont. And I'm going to talk briefly at the end about another watershed over here called Druids Run, which I'll introduce at the end. But this watershed, which is Pond Branch, is the small instrumented watershed up here in sort of the northeastern part of the watershed. Baseman Run, which is the larger watershed enclosing it. Oregon Ridge Park, which is the county park that makes up most of the watershed. Sometimes I use these a little bit interchangeably, which is a little confusing, I'm sorry. This is an area that's been studied extensively by different people over the years. It was the location of a lot of studies of geochemistry, geochemical weathering back in the 60s and 70s. Reds Wallman used it to study sediment transport dynamics, and particularly the sort of stochasticity of that. It's a N-member reference site for the Baltimore Ecosystem Study, and it's the projects that have carried that on. Particularly studying nitrogen fluxes. Peter Groffman, Larry Band, John Duncan, many others have done a lot of work there. It's also where we've done a lot of geophysical observations and a lot of hydrologic investigations over the last 10 years as well. This is a watershed in the crystalline bedrock of the Piedmont uplands, which is underlined by fractured bedrock, but has water tables sitting on top of it. This is just a bit of a close-up view of this watershed here on the right here, Pond Branch. This is a figure from one of the old geochemical studies, Cleaves et al. In 1970, which highlights an important feature of this watershed, which is that it has sort of these uplands on either side of this kind of open book part of the watershed, but then along the bottom is a swampy lowland area. And the contrast between those two really is an important feature of how this watershed works. So this is Shane Putnam some years ago when we were just starting to study this watershed, showing the line between where something recognizably soil and something that is more recognizably saprolite, retaining the fabric of the rock that's been weathered, sits quite shallow in the profile up on the ridges. So you can do it to dig far before you start seeing something that looks like rock, but that your shovel can easily bite through. Down in the valley bottoms, though, you see this broad, variable width, I guess, riparian area that's very swampy. That has multiple threads of channels running through it. And if you're not careful, you'll sink up to your knees in black, gooey, organic mud. On the left here is a perceptual diagram drawn by Emery Cleaves and his co-authors back in 1970, showing what has proved to be quite an accurate picture of how this watershed works, where you have up on the ridges a thick layer of saprolite, which transitions at some depth down to fractured bedrock. Water flows through those into this lowland area where water is fed into the channel. So the components of that I might write down for a perceptual model for this is sort of these four here. So a big sponge, a soggy bottom. We want to think about the storage in there, and then I'm going to explain what deep cuts is briefly at the end. So if we look at a hydrograph of this watershed, it's quite interesting. This is Pond Branch, that small instrumented watershed, and this is showing daily stream flow. And you can see that there is a very persistent base flow that varies something on the order of like seasonally to annually to interannually. And then superimposed on top of that is a very rapid, flashy stream flow response to individual storm events. And if we look at that base flow component at the moment, it tracks quite closely the overall water balance of the watershed. So if we construct a water balance and then from that water balance infer the total water storage and how that's fluctuating over time, it looks like this top figure here. And you can see that interannually, you get storage fluctuations of greater than 500 millimeters, or about half the annual rainfall can go in and out of storage over sort of annual timescales. And that large change in storage becomes reflected in changes in this persistent base flow, which is sort of presumably therefore leaking out of that big sponge of saprolite and fractured bedrock sitting up on the ridges. We've done a little bit of work on age traces. We've got a lot of stable water isotope data from here, which I'm not going to talk about today. But we have done a little bit of work using sulfur hexafluoride showing that the groundwater seepage coming out into the valley bottom is on the order of about 5 years old. And if that was responsible for the baseflow discharge, which is on the order of about 300 millimeters per year, then the apparent storage volume that you could say is turning over in a very rough sort of way up on those ridges is on the order of 1,500 millimeters, or about a year and a half of annual rainfall. So quite a large volume. This is hydrologically active on sort of timescales relevant to thinking about these things. And when we probe the subsurface using geophysical tools, we start to see where that storage might be held. So shallow seismic refraction shows weathering of the bedrock down to a considerable depth. So anything that's sort of blue or green, light blue to dark blue here, has a seismic velocity like that of solid bedrock, hard, you hit it with a hammer, rock. Anything redder than that has been fractured and weathered and is somewhere along the road towards becoming saprolite and soil. And so you can see that there's a good 20, or more meters of material under there. Interestingly, and this was the subject of a science paper back in 2015, it's actually quite shallow underneath the stream. And you can see it's almost like an inverted bow tie shape where you get an inverted bedrock topography. But as you go down along the channel, along the valley bottom, you can see in the bottom figure here, it's also quite variable. So the thickness of that valley fill changes considerably as you move downstream. We did some drilling up on the ridge and ran nuclear magnetic resonance probes down the borehole, which allow you to estimate the water-filled porosity of the profile. And we send this very, very abrupt transition at 15 meters, which corresponded to a transition from saprolite to fractured and weathered bedrock. And actually also corresponded to some important weathering fronts that we were able to measure by looking at the bulk geochemistry. The water table was sitting about 5 meters above that. And if you look at the water-filled porosity that's sitting above that, it sort of seems like there might be a capillary fringe of maybe like something like 5 meters or something sitting above that. It's very hard to measure that, obviously. But that suggests, that this saprolite has a very high capacity to retain water under tension. And that's going to be important in thinking about how that water moves laterally off the hill slope. And the volumes involved are, somewhat larger than what the sulfur hexafluoride suggested. But again, this is one borehole, and these things were happening at different times. We actually measured this at a very, very wet period. So maybe those differences are understandable. Moving now to the soggy bottom. If you zoom into individual rainfall runoff events, you can see there's a very rapid peak discharge, shown here in the light blue. And if you separate that from this persistent but small base flow discharge, those rapid peak discharges, the volume within them can be is always about the same percentage of the total rainfall. So our runoff ratios, unlike what Margaret was showing for Calhoun, where the runoff ratios varied sort of from 0 to 1, the runoff ratios here are almost always exactly the same. They're almost always about 4%, which corresponds to the area of these riparian zones in the valley floor. They do vary a little bit, but not more than from sort of 4% up to 6%. But there are subtleties. So we can look at the base flow, which does respond to these storm events. So there are seeps and springs all along they're quite common along the valley bottom margin. And these do respond dynamically to large events and wet periods. We instrumented 2 of them and put little gauges on them. And these suggest, by comparing what we see in those to what we see in the stream flow, that does suggest that these sort of toe slope areas are affecting the base flow recession behavior. And that's supported when we compare the storage that's implied by the streamflow recessions to the total storage. So we're sort of using the Kirchner doing hydrology backwards kind of methods. David Drali has been sort of advancing these methods recently. And these offer ways to take the streamflow recession and invert it to estimate what must be the storage volume that recession is draining. And when you do that, you get the blue line there, and you can see the variability there, the storage that's filling and draining and supplying the baseflow recessions is much, much smaller than the overall variations in total water storage in the watershed. And so this implies that the sort of the hydraulically disconnected vadose zone within this watershed is much larger than you might expect from saying, okay, we've only got half a meter of soil above the saprolite. In fact, that the storage in that saprolite is very, very significant from a water balance perspective and for thinking about recharging that base flow. So ultimately, we're able to sort of put together a perceptual model of what's happening in this watershed, where up underneath the ridges, you have a water table that is increasing and decreasing seasonally and interannually and supplying that persistent low base flow. And then you have springs at the valley margin and a saturated valley bottom. And within individual events and between events, you do get some sort of groundwater ridging at the sort of in the side slopes and at the valley margin that can generate the sort of the streamflow recession behavior that we see. Okay, so there's lots more I could say about weathering and critical zone evolution at Pond Branch, particularly focusing on Cassie Coaston's work. But I'm going to skip that and move on to a couple of other things. The first is that looking at this watershed would give you, I think, the wrong impression about how adjacent watersheds that are perhaps more human impacted behave. And one of the really important reasons for that is that across much of this sort of this mid-Atlantic New England area, there has been a lot of erosion, a lot of, there's been estimates of up to sort of like 15 centimeters of soil on average across the uplands has been eroded since European settlement. And a lot of that sediment ended up in mill dams. So these were dams that were put along sort of the Piedmont and particularly towards the fall zone. And these sort of filled up these valley bottoms. And when those mill dams were taking down, the rivers then incised into those sediments. And so now you have streams that, rather than being sort of anastomosing in this swampy valley bottom, which we see in Pond Branch, you've instead got streams and rivers that are deeply incised into legacy sediment. And so this is work that Rob Walter and Dorothy Merritts at Franklin and Marshall have been doing for many years now. And I think that creates a quite different dynamic that would be very important for this effort at thinking about perceptual models to take into account. Okay, so moving now from Pond Branch, we're going to go over to Druids Run, which is not too far away, about half an hour's drive away. So identical climate, very similar tectonic history, but very different lithology. So where Baseman Run is this biotite, plagioclase, muscovite, quartz schist basically deeply weathered crystalline bedrock. Druids Run is ultramafic serpentinite. And so that's a rock that basically, when it weathers, it doesn't produce any sand and it doesn't produce any clay. So as it weathers, it produces almost no soil. And as a result, the soils are very, very thin, if they're there at all. Bedrock is very close to the surface. It is chemically altered, but there's very little sort of storage capacity in this landscape. And as a result, the hydrologic behavior is very different. So where Baseman Run has this quite consistent relationship between rainfall amount and runoff amount, at Druids Run, it's a much more nonlinear relationship. So as your event rainfall increases, your event discharges increases much faster. And so you get much larger discharge at peak discharges, in large storm events. David Litwin went out and did a lot of field work there, mapping saturation across the landscape under different wetness conditions, and he was able to sort of estimate the extent of surface saturation in these different watersheds. And what you see is at Baseman Run, a very persistent wet valley bottom and basically dry uplands, shown here on the right. Whereas at Druids Run, there are large parts of the landscape that wet and dry and wet and dry and wet and dry very dynamically over time in response to individual storm events. And at the same time, the topography is very different. So Baseman Run has much longer and higher hill slopes, whereas Druids Run has short, low relief hill slopes. And so the question is, are these sort of things related to each other? What is it that sets the hill slope length and the degree of dissection of that landscape? And what is it that sets the extent and variability of the saturated areas? Are those two things actually related to each other, or are they sort of independent properties of that landscape? And in particular, could they be related to each other through coevolution? So what we did was, working with Greg Tucker and Katie Barnhart, we adapted a landscape evolution model and coupled it with a dynamic hydrologic model that has a groundwater surface water interaction component to it. It can do real Busenesque type lateral flows and variable source area saturation excess runoff generation. And we coupled these together and ran them for a long period of time until you get a steady state condition where the landscape and the hydrology are co-evolved with each other. And so we generate these sort of synthetic topographies from that. And so this is showing a synthetic patch of landscape with perennial stream channels, variable source areas, and ridges where you don't get surface saturation. There's a lot I could say about this, but amongst the results, we find that we can define like a dimensionless drainage capacity of landscapes, which represents sort of a dimensionless ratio of various parameters, and show that as the transmissivity increases, the drainage density decreases and the relief increases. So this sort of supports the idea that the subsurface transmissivity is actually playing a really, really important role in controlling both the hydrologic behavior and the topography itself. I won't go into the details of how we did it, but David was able to go out and take sufficient observations of the topography and the hydrology to be able to parameterize his landscape evolution model for both the Baseman Run Pond Branch area and Druids Run. And so we're able to run the model in a way where the parameters are representative of those two watersheds without calibration. And when we do that, we can start playing games and ask, is it the geomorphic variables that are controlling this, or is it the hydrologic variables? And we swap these around. So this is like a 2x2 sensitivity where we apply the hydrologic variables, including the transmissivity and the geomorphic variables of each site against each other. And you can see that where you have the hydrologic variables of Druids Run, so there's thin soils, effectively a low transmissivity environment, you get very dense drainage networks. Whereas when you have the thick, deep, weathered regolith of Basin Run, you get a much sparser drainage network and much higher relief landscape, regardless of whether you're using the geomorphic variables from either side. So this suggests that the differences between the site's topography and hydrologic dynamics can be attributed to differences in the subsurface transmissivity. The subsurface transmissivity is like the master variable controlling both of those things, the geomorphology and the hydrology. And so coming back to this Dunn diagram, this helps us sort of understand how these things are related to each other, and helps us understand that this coevolution can in fact explain something of the relationship between these. And something very interesting that comes out of this, we can take this model, we can run it for many different parameter combinations. In fact, we can sort of span the entire range of parameters of all the different parameters that the model takes. And when we do that and we plot specifically the quick flow fraction against the mean sort of relief of the landscape relative to a height scale that comes out of sort of the geomorphic parameters, we find that all the scenarios collapse onto a single curve, which was very exciting for us when we saw this. So this is sort of suggesting that regardless of what parameter set you use, all of the simulated landscapes that we can produce all plot along a line where relief and quick flow fraction have a tight sort of inverse relationship with each other. And if I plot the portion of the landscape that is variably saturated in these different cases, we find that the hydrologic processes are stratified along this line. So in the bottom right-hand corner, you have low relief landscapes with a high quick flow fraction, and a large proportion of the landscape is variably saturated. And on the left-hand side, you have more base flow dominated landscapes that are high relief. And the relief here is relative to a geomorphic height scale. I should emphasize that height scale is difficult to measure. I don't yet know how to go out and estimate that height scale easily across the landscape. And that's something I'd like to be able to do better in the future. And so why does this relationship exist? Well, sort of heuristically, and sort of in a hand wavy kind of way. By the way, I have no idea how much time I've used. How far through this am I?
You're fine. You have 10 minutes, 10 to 12 minutes.
Okay, great. So why does this relationship exist? I mean, I can't give you I'd like to be able to show you exactly how this arises. I can't do that yet. But what I can say is that it appears to represent a kind of a set of stable landscape configurations where the downslope parts of the landscape receive enough subsurface lateral flow and have a topography that generates enough of a variable source area that the colluvium that's being delivered there from upslope via diffuse geomorphic transport can be exported away at the same rate that the streams are incising. So in fact, there's a sort of a balance between the geomorphic transport in the landscape and the hydrologic transport in the landscape. So those two things have to be sort of in this sort of delicate balance with each other. And so this is sort of, these figures here are sort of showing the sort of the end members that you might get for that, for the low transmissivity case with a very variable source area, and a high transmissivity case where that doesn't vary much at all, and you get sort of springs at the hill slope margin. I should put a caveat on this, which is that this lovely relationship is entirely should be viewed within the context of the synthetic landscapes that it represents. This is a model that includes a lot of simplifications about how landscapes evolve, about how runoff is generated. If we apply the parameters, if we look at the models that are parameterized using data from these sites, we find that they sort of sit as you might expect, with Baseman Run up at the subsurface flow end and Druids Run right down at the highly variable source area saturation excess end. But if we look at where they actually sit, so we're looking at actual relief here and actual quick flow fraction, the reality is quite a long way off that line. So we're not really at a stage yet where we can say this is a relationship that we can take out into the real world and do things with. But it is, I think, very suggestive and very interesting and worth looking into more. So what we're moving towards is sort of an interconnected view of how the geomorphic, hydrologic, and geochemical landscape forming processes are interacting with each other. I haven't talked about sort of the subsurface flow and weathering process as part of this yet today, but I could. And I'll conclude by, I guess, just reiterating a couple of points. So first of all, that in the crystalline bedrock headwaters of the mid-Atlantic Piedmont, we have this deeply weathered schist with a big sponge, a soggy bottom, a large vadose zone, a large transmissivity, and low variability in its source areas. This is not all crystalline bedrocks. This is the one or two watersheds that we looked at. And in the bare ultramafic sort of site, we have thin soils, almost bare rock, and highly variable source areas. But the broader sort of idea I want to put out there is the idea that the process dominance that we're thinking about here is perhaps a signature of coevolution with other landscape forming processes, that in particular, it's strongly influenced by how those landscape forming processes control regolith transmissivity, which is affected above by erosion and below by all the soil forming factors. And those things are conditioned by the lithology of those landscapes, their tectonic history, their climate, and by human impacts, and by the ecological processes that have been going on there as well. So I could talk about a few more things, but I actually think I might stop there, and I can save things for another time if wanted.
Thank you, Kieran. You took us to a longer time frame and the coevolution of CZ hydrology and the CZ structure, which it gave us so much to think about at the system level, the long-term evolution level. I'm going to open the floor for questions now, and I don't see anything in the Q&A. So please.
If there's anything that I went through too quickly that anyone's like, didn't quite get that as well, please let me know, because I know I went quite fast.
Yes. While we wait, oh, here comes one. Larry Band says, great talk, Kieran. What were the base level boundary conditions of the landscape evolution model? I presume you had stable base levels. Can you speculate the effect of varying uplift rates and what the timescales of evolution are?
Yeah, no, that's a great question. So for the steady state models which were the ones I showed you, we have a constant rate of base level change. So basically the boundary condition of the domain is one where you could think of it either streams are constantly down cutting or the landscape is constantly being uplifted relative to some base level. The rates that we used for Pond Branch and Baseman Run in those simulations were ones derived from beryllium-10 dating of the area, particularly all the work that Milan Pavic and others have done in the area, which have done a reasonably good job, they think, of nailing down what those erosion rates are. And they're very slow. This area is not one that's it's not the highlands of New Zealand. It's a very slowly evolving landscape. The effects of varying uplift rates. It's a really interesting question. We've only really scratched the surface in trying to understand how waves of erosion would propagate up through these landscapes. And Josh Roaring's done a bit of work on sort of trying to think about how the convexity of landscapes would sort of shift as a nick point propagates up through it. At Pun Branch, you can see places where the stream is steeper and less steep, and you have to wonder to yourself, is that a nick point that's migrating through the system that represents a transient feature, or is that just a hard bit of bedrock that needs a steeper gradient in order to erode at the same rate as everything else? I guess I'm waffling a bit because I don't have a great answer to your question, except to say that we hope that the stochastic variations in base level change that might have occurred over time merge together sufficiently that the argument we're making is at least useful.
All right. Here's a question from Shan Zudima. I may pronounce your name incorrectly. I apologize for that. Based on your landform evolution modeling work, what are the timescales you would expect coevolution to occur? Would this be consistent with some of the land use histories you described, like mill dam infilling and down cutting?
One of the nice things about doing steady state stuff is you don't have to think about that too much. There are multiple timescales involved, and they all interact with each other. The timescales involved in a stream cutting down are often quite rapid relative to the rates of soil production, which is very rapid relative to the rates of overall denudation of like ridges. So under transient conditions, you'd find all of those things sort of happening at the same time, or varying in response to different timescales of variation. We actually tried putting in, we initially included a soil development, a sort of an Argenheim-Sack type soil production function in the model, and it produced such numerical instabilities that we abandoned it and just said, okay, we're just going to assume that soil thickness is always constant, because it was too much to bite off to try to overcome those numerical instabilities. I would say that the timescales of which the mill dam sediment infilling has occurred are very rapid relative to the scale of which such changes would propagate up into the hill slopes. So I wouldn't expect those. I generally wouldn't expect those sort of valley bottom filling and draining things to have had a significant effect on the uplands yet. But the erosion from the uplands that produced those sediments certainly could.
A related question from Walter: what's the sort of rate of change in process dominance we can expect when catchments adjust to human impacts like the mill dams you mentioned?
Everyone wants to know about the transients. I would say that there's so many things I could say about this, but let me put it this way. The ability of the landscape to resist change depends on its ability to get water underground. When water is flowing across the surface, you're more likely to have erosion. You're more likely to have overland flow. If you're in a landscape-dominated environment, you're more likely to saturate the landscape to the point where it all slips off. So being able to drain water rapidly through, but not so rapidly that you cause erosion, through subsurface pathways is what you need to do to maintain a relatively stable upland configuration, at least. So all the landscape changes that make the soil thinner or make it water more likely to run over the surface rather than go through a subsurface pathway, are going to both, change the hydrologic processes and change the rate at which all the other processes that are related to hydrology are evolving. So, over versus under is an overly simplistic way of thinking about it, but is perhaps a starting point.
Next question from Martin. Can you talk a little bit more about the challenges in mapping that hand over the scaling factor spatially, the Z prime over HG spatially? You skipped, and that's one question. And then second, you skipped over the differences between model world and real world quite quickly, and I'm keen to learn more.
So there's multiple problems. I'll tell you 3 of them. The first one is that you need to know an effective, well, first of all, you need to assume that, the 0th order thing is that you would need to assume a steady, some sort of geomorphic steady state, and which everybody is putting up their hand saying what happens when things are unsteady for a very good reason, but it's hard to sort of say when landscapes are in steady state or not. The second is that, related to Larry's question, you need to know what is an effective uplift rate or overall denudation rate. That's one of the, there's 3 parameters that go into that height scale: the uplift or / denudation rate, the diffusivity, which is the rate at which those sort of upland colluvial processes are smoothing out the landscape, and a steepness index, or a sort of a fluvial erosion parameter, which basically says how good is water at cutting down streams. The diffusion one you can get from measuring the curvature of hilltops, as long as you know that uplift rate. The incision one you can get from measuring the concavity of stream profiles, but there's lots of problems with how you do that. David Litwin, who was the PhD student who was doing that work, is at the moment putting the finishing touches on a paper sort of showing that how those diffusion and curvature things interact and make it actually really hard to estimate either of them. So look out for that paper. But it's a delicate measure of the curvature of the landscape, which is both of them are delicate measures of the curvature of the landscape, which is a notoriously difficult thing to measure in a consistent way. But that uplift rate one is also just, we need to know effective denudation rates across the entire landscape, and I don't know how to do that.
I have a question to all the speakers. I look at the conceptual diagrams or perceptual models. All the spatial scales are tens of meters, hundreds of meters. It seems that this is sort of the fundamental length scale, spatial scale, that processes occur, processes are described. We observe them at this scale as well. And now we have to build a model of the continental scale. And currently the water model, the national water model, is 1 kilometer, Martin, correct me, something like that. We have, we are at this step right now, we are trying to really not worry about that first, and I really think about what are the actual processes that has to be represented in order to get the flow right, summer, winter flow, the storage right, explain the dynamics of water fluxes. And next stage, eventually our community goal is to build these processes into these impossibly large models, but we have to. So there is a huge scale difference. It is just practically difficult to describe tens of meters. I saw some graphs, 70 meters, 100 meters, 120 meters, 240 meters, Kieran, your graphs. And so this is a fundamental challenge that we have to also face. So any comments from you speakers, I would appreciate, and we have plenty of time to discuss that in the afternoon, but I would really want to put that on the board now.
Well, if I could probably get started by saying that I think that the scale depends on the process. You know, if you were, in sort of the geomorphology landscape evolution context, and that's what I've been talking about, so that's where my head is at right now. Channel that hill processes versus hill slope processes are very different from each other, and they're both very important. Landscape evolution models, you know, the ones we've used, are very naive about the existence of channels, and make some very coarse assumptions about that. I think I don't think it's useful to sort of think about, okay, we're going to divide the landscape up into chunks and assign a model to a chunk. You know, I think that the kind of representative elementary watershed idea of saying, okay, we're going to divide the landscape up into some sub-watersheds or some hill slopes, and then parameterize how the parts of those, regardless of how big they are, how the riparian zone, the channel zone, sort of the shallow subsurface, the deep subsurface, how those pieces of them interact, according to some perceptual model, is the more important thing. You know, and that might mean that some of those pieces are much, much larger than other pieces, because the processes aren't operating at those different scales. But I think hill slopes, I like hill slopes.
I love hill slopes too. I think they're some of the more interesting scales to study at. I will say, I also really value people who, like, I think maybe between those two scales. So there's been a lot of work that has like used USGS stream gauges to look for like statistical relationships between a lot of our like spatial products that we have in the stream flow regimes that are observed in those gauges. And I feel like we can get a lot of process information from those studies, and they're nice because they, I think, connect between these two scales that you're talking about. So I would say, like, yeah, people who are maybe looking at that intermediate scale might be great people to bring into this type of conversation to help us connect the hill slope process scale to these bigger models.
In a way, doing hydrology backward, reading from stream flow back out to the catchment processes. Amy, you have something to add?
Yeah, so I'm not clear why we can't do it the way it's proposed, where we are. To back up, I guess I don't see how we can get away from dividing the landscape up into little chunks, and because different processes are so different in different areas, and to get the flow right, I think that's a good way to proceed, and I think how we are proceeding. So, but the mesoscale that you were just alluding to, Margaret, is something I just tried to grapple with at the end of my talk, and those processes certainly, yeah, we need to step back and have a larger scale bar on our perceptual diagram. So, go ahead.
Well, I was just thinking, I mean, it's certainly the case that if you divide the landscape up into, say, hill slopes, you know, a scale at which these sort of conceptual diagrams, these perceptual models, the scale at which we draw them of an individual hill slope, is probably itself in some ways too small, because we can't determine the parameters for every single hill slope. But what we might be able to do is to say something like, within this area, there are a sort of a stochastic ensemble of hill slopes or of landscape units, that each of which is some variation on this theme. And we can try to say something about how its properties, the joint distribution of all of those properties within that area. I think we have to account for the heterogeneity, but do so in a smart way, not where we have to try to measure everything, but something that is allows for the stochasticity without having to measure everything. I think it is convenient that hill slopes arrayed around a channel network behave in some way independently of each other. That allows you to treat them as an ensemble, and that could be useful. I think that the challenge becomes when you start thinking about the valley bottom. Once you get down to the valley bottom, you get longer range interactions. You get losing reaches and gaining reaches, so that linear independence of all your ensemble of hill slopes within an area might break down. So it may be that you have to do something a little bit different between the uplands and the lowlands.
I'm going to inject what Larry Bend just wrote to jump ahead to the utility of these studies to improving national water model and other models. Are there key metrics emerging from your work that can be important diagnostics for evaluating model performance? Maybe this is a question for, I think Jamie's earlier slides showed how poorly the national water model was performing in the Sleepers River watershed. Maybe this is a question for both Jamie and Martin. And Katie, where's Katie? Is stream flow the still the metrics?
Yeah, I agree with what Kieran was saying about we need to kind of find some uniform, concepts and flow mechanisms that, because we can't, divide the world into every single hill slope. So what you're talking about is more what reminds me of the top model approach. Like there's different landscape metrics that sort of represent one part of the landscape that can be sort of integrated over the entire watershed. But there'll be, you might have many different processes we need to kind of bring together. But hill slope, I love hill slopes too, but a hill slope in Vermont is going to be way different than Margaret's hill slope in California. So are there different groups of processes that we can focus on in one part of the country and make the national water model better that we don't need to consider in other parts of the country and vice versa?
And Larry said, or for everyone. The question is for everyone. Katie?
I would just add that's really what we're aiming to end up, where we're aiming to end up is a better understanding of the processes we're trying to capture and come up with diagnostic metrics to evaluate whether our models are capturing those processes. We're not there yet, but that's a significant part of this project, is aiming to get there. So we'll be happy to take any suggestions on that, but as we synthesize what we learn from all these experts, that'll be a core part of this project, to try to figure out how we measure how well we're doing in capturing the dominant processes in the models. Oh, good question.
I'm going to hand this over to Julia now. Perhaps
Yeah, thank you
go
so
ahead,
much.
Julia.
Yeah, so we're about 4 minutes out from the hour. A huge round of applause to all of our speakers and also to all of you who attended for contributing with your questions. We really appreciate you all taking the time this morning to work with us on this. That brings us to, we're about 4 minutes away from a break. We're gonna have a 1 hour break, so stretch your legs, get some lunch, depending on where you are. And then we'll reconvene in a meeting room that is separate from this meeting room. The link to access that, if you don't already have the connection, information is in the chat here. We hope that you'll join us. And in that meeting room, we'll have another 3 hours. That'll begin with some questions to the group as a whole. And then we'll be breaking up into breakout rooms to start diving in to some subregions.
I realize I missed one question from Paul Brooks. Can I just put it in here? Discussing spatial scales follows naturally from perceptual spatial cartoons. How do we include temporal dynamics and temporal scales processes? Temporal scales provide constraints, but are difficult to represent in catchment, watershed, hill slope, landscape cartoon. Absolutely, yes. I think a temporal part is less of a challenge for large scale models. We do have very high temporal resolution. The cartoons are difficult to do. That's why I think Margaret and Jamie, they all had low flow, high flow, summer and the winter conditions, snowmelt driven conditions, summer rain conditions. So perhaps that offers a path forward so that we can have, the regimes, not just in space, but also in time. And so I think keeping that in mind in our later discussions will also be helpful.
Yeah, Yim, can I just add to that?
Please.
And I would say that the temporal component can be very important if we're interested in simulating the processes on longer timescales, rather than prescribing the details of the landscape from the geophysical attributes that we have. And to the extent that that's important for answering some questions on decadal to centennial timescales, I think we need to think about representing the longer term processes in our models as well. I'm not sure if that's where Paul was going, but I think it's important.
And just a reminder, please register for this afternoon session here. Julia put a link to register on the chat box. And so we will see you at 2 o'clock. And then when we come back, we're going to decide on breakout rooms. We'll see you. And then we can really break out into smaller groups and smaller rooms and smaller, we can really start with some templates and then fill in more conceptual models. And so we'll see you at 2 o'clock. And panel and speakers, please stay on a little bit.
Thank you, everyone. Yep, so
Thank
we will
you
be
so
seeing
much.
you. So in the meeting room, it's different setup from this. You'll be able to unmute yourselves, have your video on, and we look forward to chatting with you then. Thank you so much.
Bye. See you soon.
Just quickly, we've got